All right, in this next segment, we're going to be going beyond what Lewis structures can tell us. This simple, relatively simple Lewis structure theory of bonding, to see what happens in the three-dimensional shapes and how these ideas can help us understand three-dimensional shapes of molecules in many cases. So the learning objectives for this segment are to predict the molecular geometry around central atoms with Lewis-Stock structures using VSEPR theory. All right, so VSEPR is valence shell electron pair repulsion model. And what that is a way of understanding how the results of the Lewis dot structures help us understand how the molecules are actually shaped. Because how a molecule reacts and interacts with other molecules depends to a large extent on its shape. Okay, so the basic principles are pretty simple. Electron clouds repel because of negative charge and Pauli exclusion principle. So clouds of electrons don't like to be near each other. Regions, so therefore, because of that, regions of electron pair density, and these include both bonds. A bond is essentially, a concentration of electrons, and non-bonding lone pairs, they each repel each other. So the best molecular geometries are those when these regions of electron density are as far away from each other in 3D space as possible to minimize repulsions. And that's really it. That's the idea, and it works remarkably well for a very wide range of molecules. So steps for determining molecular geometry based on VSEPR theory. Determine the Lewis dot structure. So first you have to get the Lewis dot structure because you have to understand around each atom how many bonds there are and how many lone pairs there are. So count the number of electron densities around the atom of interest. That includes both a bond and a lone pair. Arrange the electron densities to be as far apart as possible. There's going to be a little more to this because you'll need to take some facts about geometry into effect, but basically that's the idea. Lone pairs take up more space than electrons in bonds because in a bond, the electrons are sort of confined to a volume between the atoms, but a lone pair, is just sort of unattached. It can spread out a little bit more. Okay, so let's look at the preferred electron geometry. So first, what we have to do is look at the possibilities given that there are n electron clouds. So for n equals 2, to be as far apart as possible, it's going to be linear, right? For 3, it turns out the farthest thing can be apart in three-dimensional space is actually still confined to a 2D plane, but it'll be at 120 degrees. So they're as far apart as they can in the 2D plane, and they'll be 120 degrees apart. For 4 electron shapes, then it turns out that the farthest you can get is 109.5 degrees, an equilateral tetrahedron, like 4 equilateral triangles glued together. For 5, this is a little more non-intuitive, but it ends up being what's called trigonal bipyramidal. So it's bipyramidal because you get a pyramid on top, trigonal, a pyramid that instead of a tetrahedral pyramid, you have a pyramid with a base that's a triangle, and there's 2 of them stuck on top of each other, right? So it's trigonal bipyramidal. 2 pyramids that have bases that are triangles. And so there, around the equator, then they're spaced 120 degrees, and then the ones in the perpendicular to that plane are 180 degrees. So essentially something linear superimposed on top of trigonal planar. And finally, if there's 6, it's octahedral. You basically just have, like an X, Y, and Z axis. And those are as far apart as these electron densities can get in each of these cases. Okay, so those are the basic geometries. So let's look at some examples. So what are different ways you can have 2 regions of electron density around a central atom? Obviously, if you have just 2 atoms, it's always linear, right? Because 2 points define a line. So we'll go up to at least 3 atoms. So there's at least 2 things stuck to a central atom. So CO2, that has 2 regions of electron density, right? There's 1 double bond here and 1 double bond here, and there's no other regions of electron density around the carbon. Therefore, the CO2 molecule is linear with a bond angle of 180 degrees. And that's exactly what is seen in experiment. A CO2 is linear. A hydrogen cyanide molecule is linear with a bond angle of 180 degrees. In this case, the carbon has 1 triple bond and 1 single bond, and but experimentally, this is a linear molecule. So that's another example where basically the 2 possibilities of having 2 regions of electron density. Okay, so now we're going to move up to 3 regions of electron density. And there's 2 possibilities here. It could be that you have 3 bonds. For example, formaldehyde is trigonal planar with a bond angle about 120 degrees. Yeah, so you've got the double bond here from the C to O, and then you have 2 single bonds to the H's. And what we see is that these are slightly smaller because the double bond takes up a little less space than the single bonds of the hydrogen. But it's nearly 120 degrees. I mean, it's a little more complicated than that. We're dealing with Schrodinger's equation, but what we guess by VSEPR theory is that they should be about 120 degrees, and they are about 120 degrees, and it is, you know, flat in plane. However, SO2 has 3 regions of electron density in a trigonal plane. It has a bond order of 1.5 to each of 2 oxygens, but then a lone pair. And so in this case, we have roughly 120 degrees between each of the electron densities. But if you sort of are just looking at the atom, the atoms in the molecule themselves, it looks bent because you don't see that electron pair. So you have a bent angle between the 2 atoms. So that's the 2 cases you could have with 3 regions of electron density. You could either have 3 atoms, in which case it's trigonal planar, or you could have a bent molecule because the 3rd region of electron density is lone pairs. You can't really have 2 regions of electron density and 1 atom because that's just 2 atoms, which is a line. Okay. So I'll pause a little editorial comment here. Like, why do we care about these? It turns out that the shape is important for a lot of molecular properties, as we'll get into at the end of this this segment, maybe in the next segment, and then in chapter 12 later on as well. Okay. Okay, so we handled 3 regions of electron density. Let's go up to 4 regions of electron density. So methane, a tetrahedral with a bond of 109.5 degrees. So methane has, its 4 regions of electron density are 4 bonds. The 4 hydrogens, and they're all equivalent. Like by symmetry, they're all exactly the same. And so they'll be spaced as far apart as you possibly can get, 109.5 degrees. Ammonia has 4 regions of electron density, 3 bonds, and then 1 lone pair. Now remember, the lone pairs take up a little more space, and so the 3 hydrogens bonded to the nitrogen are squished a little more together because they're being pushed away from that region for electron density. And then also you could have water, which has 2 regions of electron density and 2 atoms. And there you have 2 lone pairs that are taking up quite a lot of space. And so the hydrogens are pushed together even more. So the water angle is 104.5 degrees. So those are the 3 possible cases if you have 4 regions of electron density. Again, the other case, 3 lone pairs and 1 atom, that's just 2 atoms again. So those are the 3 cases. And you see all of these quite a lot. These are all very common configurations to have. All right. There are some that are a little less common, but still very possible. If you have 5 regions of electron density around a central atom, remember there are many cases where if you have an expanded octet, then there are many cases where you can have more than 4 regions of electron density. For example, phosphorus pentachloride. You have 5 identical 5 identical chlorines that are bonded, and so the furthest apart they can get is trigonal bipyramidal. That was one of the shapes with n the shape with n equals 5. Sulfur tetrafluoride, on the other hand, it also has an expanded octet, but once you do the Lewis structure, you find out that there's 4 bonds to fluorines and then 1 lone pair. And so it turns out that the question is, where does the lone pair go? So lone pair will go where there's the most space. If the lone pair was up here, then that would only be 90 degrees to these other 2. But if the lone pair is over here, then it's 120 degrees from 2 of these. It's still 90 degrees from these, but it's 120 degrees away from the other equatorial one. So when you have a trigonal planar, then the place that the lone pair likes to go is exactly here on the axial direction. So it goes here. So this looks like a seesaw. You can imagine drawing guys playing on the seesaw here. Whee! All right, so you gotta look to the side, but it's a seesaw. There you go. And the lone pair is here. It turns out that that this angle is actually slightly less than 180 degrees because the lone pairs are pushing it out of the way, but it's pretty close to 180 degrees, like 174 or so. Okay, so that's the next possibility, the possibility where you have one lone pair and 4 atoms. So let's just keep enumerating all the possibilities. You could have 3 atoms and 2 lone pairs, like in carbon trifluoride. And in that case, the axial plane, those axial atoms are the ones that are furthest apart from others. And so if you take 2 of those away, what you're left with is essentially a T-shaped molecule, right? You just have those axial 2, the lone pairs are here, and you've got the other molecule there. So it's T-shaped. And finally, you have the case of just of 3 lone pairs and 2 atoms. And in that case, again, you have all 3 of the lone pairs along the axis, and so the atoms themselves are arranged in a line. So it's another possible linear arrangement that you can get. In this case, it's the iodine 3 ion. So those are the possibilities if you have 5 regions of electron density. Again, you'll only see this in molecules where the central atom can have an expanded octet, because you need an expanded octet to have 5 regions of electron density. All right, 6 regions of electron density. Remember that the basic shape there is the octahedral shape. And so you have the possibilities of just having 6 atoms, like in sulfur hexafluoride. And then that's exactly the way you imagine, just X, Y, Z, straight up and down. And then the next possibility is 1 lone pair and 5 atoms. And in that case, it turns out that the axial direction is the most favored one. So you end up cutting off, well, I mean, actually, what am I saying? It doesn't really matter, right? If you look at it, all of the directions are exactly equal. And so since all of the directions are exactly equal, it doesn't matter which one disappears. It is replaced by a lone pair. Any of them could, and if you delete any of those 5 and put a lone pair in its shape, you'll get something like this, that's square pyramidal, right? Because now it's a pyramid, but you've got a nice square at the bottom, just like the pyramids in Egypt. So square pyramidal is the shape there. And finally, we have xenon tetrafluoride, which is a real molecule. And it turns out that once you have 1 lone pair axially, then the next place for 2, they want to be as far apart as possible. And so the other lone pair goes along the other axis, and you have essentially a square planar molecule. It looks like that. And so those are really options. I don't think there's any cases of 6 regions of electron density where you have 3 lone pairs. I'm not aware of any molecules like that. So this pretty much covers all the possibility. And most of them are, if you don't have an expanded octet, you won't have 5 or 6 regions of electron density. So those are the shapes, and that's it. That explains a lot of the shapes you see. Those basic principles. Electron groups want to be as far apart as possible, and lone pairs take up slightly more space. And that explains most of these molecules. Let's go on to some more complicated ones. What about iodine hexafluoride? This one we have to dig in and actually do the Lewis structure. We didn't do that one before. So let's see how many electrons it has. Well, it's going to be 6 times 7. There's 6 halogens there. So it'll be 42 electrons. And we know that the iodine has to be in the middle. We draw 5 fluorines bonded to it. So we know it has either 5 or 6 regions of electron density, but we don't know which until we draw out the Lewis structure. So we draw in 10 bonds. That leaves 32 electrons left to place. Now we notice there's 5 fluorines, and each fluorine can take 6 electrons around it. So if we were to just put 6 electrons on each fluorine by 3 lone pairs each, that leaves 2 electrons. And so those 2 electrons would have to go on the iodine. Let's draw just to be completionist, we'll draw the full Lewis structure with all the ions. Okay, so that's what it's going to look like. And so it has the overall electron geometry of octahedral, since there's 6 groups, but one of them is a lone pair, and so it's going to be square pyramidal. Right, so it'll be the, if we were to draw it, I'm not a great 3D drawer, but it'll look like this. And this fluorine will be up, fluorine, 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 and then a lone pair down here. So it'll be square pyramidal what it will be. And you know, the fluorines will be tilted up just a little bit because that lone pair takes up a little more space. Okay, so we've done that one. Let's try another one. How about tungsten hexachloride, also a real molecule? Let's see how many electrons there's going to be. Well, we've got, so we've got 6 from the tungsten. You look up on the periodic table to check that. 6 valence electrons of tungsten, 6 times 7. So there's 48 total electrons. And tungsten is the least electronegative. CFCl, Cl, 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 Cl. And so we have 6 bonds already. That leaves 36 electrons left. Now we know generally for halogens, we're going to be putting 3 lone pairs around each of them. Generally, if they're on the outside, halogens obey the octet rule. And so 6 times 6, 36 electrons, there's 0 left over for lone pairs. So that's actually what we would expect to see. And each of these formal charges, this is probably, seems pretty stable with the respective formal charges, because the tungsten, it has a valence electron of 6 minus 1/2, 12, because it has 6 bonds, 0, and each of the chlorines have, if you look at their formal charge, it's 7 minus 1/2, 7 minus, sorry, let's start with the 7 minus 6 that are in lone pairs, minus 1/2, 2, equals 0. So we have a formal charge of 0 there. So yeah, the formal charges are all 0. So we have 6 electron groups, so it should be octahedral. Again, which is what we see, which was like experiments show as well. So that is how the molecules are, the atoms are arranged in space. And that's, it won't cover all the possible cases, but it covers most of the cases we see. And we'll talk more about molecular orbitals and talk about some of the exceptions there, but it's a very good guide for how atoms arrange themselves in space.